I just learned about PID control, and I liked how it worked on simple systems. But will this work on more challenging systems with constraints and multiple variables? For example, I was thinking of my car and the fact that I can steer, change gear, and move the throttle. How would PID deal with all of that? Also, why do I have to wait for a hill and then for the car to slow down before the controller responds? That's like driving using the rearview mirror, always reacting to the past instead of anticipating the future.
Yes, and even worse. With steering, you will not respond to the corner until you are on it and will likely go off the road. However, I have a solution for you. Human drivers look through the windscreen. That is, they look into the future, not the past. We need to think about how we can get our feedback loop to do that.
That's a good plan. I can see that I anticipate all the time before deciding what to do. But how do I capture my cleverness and put it into a mathematical algorithm that can control the car automatically?
Well, let's be more precise about what human drivers do. We have some internal measure of what good behaviour is, and then we select the control actions which we expect will lead to the best future behaviour.
Okay, so I guess we need to decide what we mean by good behavior. For example, getting to the target speed quickly, staying at the target speed, staying within the lane, not crashing into walls or pedestrians and so forth.
That's right, but you are still being too vague for decision making. We need to be a lot clearer on what we mean by getting to the target speed quickly and staying in lane. For example, do we want to accelerate in 2 to 3 seconds or 10 to 15 seconds? And how tightly do we want to stay in lane? Is a drift of 50 centimetres okay?
That makes sense, but why not just go as fast as possible and keep to the lane as tightly as possible?
Because nothing comes for free. To get very fast acceleration, we need very large throttle movements, which uses a lot of fuel and can be damaging to the engine.
So you're saying we need a trade-off between fast and accurate speed control and how much fuel we use. I guess that makes sense. I do that all the time.
You've got it. And that is what defines a predictive control approach to feedback. We define expected performance in the future and choose the control actions that we expect to optimize that.
Predictive control sounds very clever. Is it used much in industry?
Oh yes, and it is even cleverer than our example. Our predictions and optimization can take account of any limits in the system, such as lanes in the road, obstacles, limited engine power, and more. Moreover, the optimization can trade off between performance in different states for systems with multiple dynamics: roll, pitch, yaw, speed, etc.
Does that mean that aerospace examples are a core use of predictive control?
Ironically, no. The biggest use is in the petrochemical industry, where the processing requires the simultaneous movement of multiple controls alongside an equally large number of different state requirements: temperature, pressure, concentration, level, and so on. The decision-making needs to allow for constraints on many things, such as actuator movements, pressure limits, temperature limits, and more. Humans cannot manage this, so we need tools like predictive control. Since becoming popular in the late 1980s, predictive control is probably the second most widely used approach in industry after PID.